Yo, you're right. It's Tommy Allen here, and today I wanted to show off my kind of native Unreal occlusion system that I have built to kind of get around the problem of occlusion. So a lot of the times in games, the way it works in straight lines, if you can't see it, you don't hear it. So we've got to think of ways to get around it. We can ray trace, kind of do a kind of transmission through a building. I've seen lots of different examples. Wise reflect, kind of let sound bend round, which is quite cool. We got Project Acoustics, which kind of got to bake and then send off. But with this system, it's kind of all to do with the player already built in. There's no extra steps, which I quite like. So I'm just going to show you what it does first. So just ignore the green ray traces for now. I'm going to turn them off. Let me go into edit the blueprint. I am going to turn off these, so compile. So, compile. So, what happens first is we've got a bunch of these balls and they kind of scatter around our player. And when we go into volumes, it shrinks. So that's the reflections that our ears can see. Okay, and they kind of run along the walls as well. So where we're looking, that's where a sound is going to bump off the ball and come back to us. So, and they're going to change. So if we come right behind an object, there's going to be a lot less chance for the sound to actually physically hit us. Okay, as we move away, sound can then come round and loop over. Okay, if we come into like a small tunnel, okay, we're not going to be able to hear much, but we will be able to hear that little ball at the end as a reflection. So in the game, you might still be able to hear it. There is a tiny dog barking from the other side of the wall, and that's occluding round. So what I'm going to do, I'm going to go back into the blueprint, and I'm going to turn on these ray traces so it's clear what's happening. So what's going to happen is we've got this ball sound source, and it's going to draw a ray trace to every single one of our balls. And with that, we can then kind of say, is it being occluded? Okay, how many of these balls can it see and hit? And that's going to give us, or for me, I put a low pass and a volume kind of RTPC to kind of change how much is being occluded. And then also, if or one of our balls hits a static mesh and we get a line trace to it, I calculate a reflection. So you're going to hear early reflections and occlusion all at the same time, which is pretty cool. So you're going to hear early reflections and also occlusion at the same time. So I managed to make two things at once, kind of by accident. So let's see this in action. So at the minute, we can't really hear or see anything. As we come around, and that we've got that kind of outdoor echo. There's no reverb on this. It's just all the reflections coming back to us. If we come round into our space, there goes the ball. Which sounds, it works. It's an occlusion system that's kind of free for all. Oh, there goes our ball. So yeah, I just wanted to kind of show off that little occlusion system that I made. It's really, really cool. So yeah, that's it. That's just an idea to kind of generate occlusion. What I'm actually doing is, because ray tracing is computationally expensive, I'm actually running it at a certain tick rate, and again, I'm looping them all. So there's only ever one ray. No, there's only ever two rays, one from the ball, one to the player. And well, that means I'm not having 35, 36 rays all fire at once, which would then double up to be 72. What it's doing is kind of one loop, but it's looping really quickly, which kind of gives us a bit less computational intensity. there's a few improvements I want to make to it. I think with the ball area, we can kind of estimate the volume. I've not taken it that far yet. And then kind of that drive a RT PC for reverb. What also the ball coefficients do. I'm going to pull up the blueprint. And no, it's not in here. It is in the player blueprint. Hold on. And I've actually got a indoorsiness coefficient. I didn't want to use an outdoor coefficient. Project Acoustics uses that. So if I go to third person, blueprint, edit, and where is it? I have indoorsiness coefficient here. So let me just run that through a. Oh, I got the print string already. The print string already set up. Okay. So these values you're going to see. Oh no, sorry. Stop. I'm just going to hook that up to there. Okay, compile. And it's going to rate it out of 1 to 0. Okay. Ah! What are you doing to me, man? Indoorsiness, array, average array, float, printing string. Ah, indoorsiness curve. In time. This should now work. Okay. Compile. There has to be. Ah, it's coming out of text color. Print string. That's why. Here we go. So there is another print string going on. Hold on. I'm going to pause the video. We don't need this one. That's pink. That's not driving anything. Let me take that one off. Take that one off. That's one print string out of the way. Compile. Let's go in here. Where is the print string? There's that bloody print string. So I'm just going to unhook this. So, yeah. So another thing this blueprint does, it calculates indoorsiness. I didn't want to have an outdoorsiness coefficient. Project Acoustics already has that, so I went for indoorsiness. And what it's going to do is it kind of calculates how many of these balls are, hitting a surface. So as we start to come out, we're now pretty outdoorsy. Okay, but we're still surrounded by walls. So I've then running that through a curve to generate it. And as we come in here, yeah, that's pretty outdoorsy. I wouldn't call that very indoors. Okay, that's why we're getting 0.6. Come outside. Oh, our occlusion's going. And then we're really outside and it's like 0.1. And I want to run that to kind of generate RT. Okay, or reverberation times. So that's pretty sick. I hope you enjoyed it. There's, a lot of other things that I want to build out of this, but just a small demonstration to show you what I've been working on. So I hope you have a great day and see you in the next one.